Okay, we're actually going to begin today's lesson with an example. The last day you were here, so 2 days ago, you did an exploration that was an introduction to an idea of a type of problem that is called related rates. In related rates problem, we're going to have multiple rates. Another word for rate or rate of change is derivative. So there's going to be multiple derivatives in terms of different variables, and we're going to relate them to each other through an equation. So our first example in the book says, assume that the radius and height of a cone are differentiable functions of t for time, and let v be the volume of the cone. Find an equation that relates dv dt. Remember, d we can think of as meaning change in, so this is the change in volume over change in time. So how is the volume of this thing changing as time passes in relationship to dr dt and dh dt, how the radius and the height are changing in terms of time. So what we have is a cone, and the radius is growing or shrinking, and the height is growing or shrinking, and as these things are changing, the volume will change. And we want to relate the change of the volume to the change of the measurement, the height and the radius. So, got a cone, radius, height. What's an equation for volume of a cone?
Pi over 3r squared h.
Oops. Okay, so 1/3 pi r squared h is kind of a normal way to write a volume equation, or pi over 3 radius squared times height. Pi r squared is the area of the circle times height. And then when we bring it to a point, instead of bringing it straight up like a cylinder, that cuts the volume down to 1/3. So what we want to do is relate the volume in terms of time. So we're taking our derivative in terms of time here to each of the variables that are changing as well. What rule am I going to need? A chain rule and a product rule. That pi thirds can just kind of hang out in front of this whole thing because it's a constant. But then we have h times r squared. So we will need to use a product rule there and a chain rule as well, because we're not taking our derivative in terms of r or in terms of h or in terms of x. We're taking it in terms of time, something that's not even in this problem directly. So product rule first, so h. D second, what's the derivative of r squared? 2r, but we're taking it in terms of time, so we need a dr dt. Kind of like when we did that implicit thing, and every time we took the derivative of a y, we needed the dy dx. Every time we take the derivative of any variable here, we're going to need that variable in terms of time. Plus the rest of the product rule, first d second plus second, and what's the derivative of h? dh dt, because it would just be 1, and then we need the derivative of the height. So then typically a problem would give us some information and say, what is the change of volume at the time that the height is this and the radius is this and the radius is changing this way and the height's changing this way, and we would go and start plugging in all these values. Okay? But this question just wanted us to set up the equation. Questions? Okay, so a strategy for us is going to be that we're going to read our problem carefully, copying down any values, defining some variables, and deciding what it is that we're supposed to be finding. While we're doing that, drawing a picture might be helpful, because then we can just label variables in the picture as they occur. We're going to write an equation that relates all the variables together. If there is any value we're given in the problem that's not changing, something that's staying constant the whole time, we can go ahead and plug that number in. But if a value is changing, we do not want to plug it in yet. Then we'll take the derivative of the equation with respect to time. So that's that d whatever variable dt for every variable in the problem. After we take the derivative, we'll plug in anything that has a changing value. And hopefully, there's only one thing left at this point. If not, we might need a secondary equation. And then we'll solve for that thing that's left. Making sure that our answer makes sense. If something should be getting bigger, or getting smaller, or faster, or slower, that we're getting the right type of answer we think we should be getting. And making sure to include units.